These are some additional Seattle criteria which are not in the manual, but they're just suggestions for good practice. Providing that 2-foot firm shoulder where you've got parking. Your kind of uncompacted bioretention soil media can be kind of soft, and so if you've got that right up to curb and somebody steps out of their car, that's not going to be a good firm surface for somebody who's arriving to a party in their fancy shoes. So maybe you want to think about firming up that shoulder, and then grading at, well, you see there 4-to-1. Actually, I misspoke earlier 3. It's actually 4-to-1 at intersections, so it's extra flat. And so these are just some Seattle criteria to think about. Or rockeries greater than a foot high need to be at least 10 feet from the curb edge. I'm sorry, I misread that. These are some Seattle criteria about rockeries. Having a max 4-foot depth seems reasonable. We don't want these to be cavernous or deep. They can be kind of disruptive. More importantly, I think, is selecting your plant material that is responsive to kind of your cross section, so that if you've got a deep cell, you've got tall plants, but you're thinking about vision criteria. So these are just some Seattle criteria. They've been at this longer than most and have developed these criteria. There's a lot more in their standards. Also, some typical sections out of Seattle's manual. I'm not going to belabor these too much. These are available for review. Just looking at the typical geometry that they like to see. I think in particular, I would draw your attention to that 2-foot zone behind the curb, and then also draw your attention to that berm on the right-hand side, about where you've got to do a little berming to achieve your freeboard. Just kind of how that looks would be something that worthy of a little study if you're interested in kind of learning from their experience. And then this is with and without a curb. Again, just some geometry to consider. How their rockery wall interfaces with their bioretention soil media, also something worthy of a little bit of study if this is a condition that you wind up with on your project. Having had this condition on projects I've worked on, thinking about where you're going to put your wall drainage is of particular importance. Thinking about how you wouldn't throw your typical 4-inch slotted pipe down there below your bottom of your rock wall like you normally would, because you're basically going to dewater your cell potentially prematurely. So you want to think that through. Think about how that permeable drainage behind your wall is going to communicate with the ponding depth in the cell. Design conditions to think through. We don't have the time in this setting to dive into them in detail, but we do dive into them in great detail in the advanced training. We were fortunate enough to work with the city of San Francisco to help them develop their green stormwater standards, and this was out of that work. So things to note here. One, it's in a parking location. So because we're in a parking location, you can see we've got the courtesy zone provided there between the curb and the cell, so somebody can get out of their car and stand there. We did provide the little trench drains that you can see as an inlet with the little splash pad and the rockery on the left-hand side of that cell that's a little more dark. And then no overflow structure. We just have another curb cut on the basically the downslope side. And so it's just basically water in, water out. Anything that doesn't get infiltrated in the cell just kind of continues on its way. You can also see the breaks on the sidewalk side to let the sidewalk water flow into the cell as well. And you can go on to San Francisco website and pull up the whole bunch of details and all the different conditions. These are some cross sections for their planter wall, again out of that same work, kind of showing the penetrations for both the sidewalk side and the road side and how they relate to get the water into the cell kind of from both sides. I think we talked about filter fabric a bunch. Please don't put filter fabric in your bioretention cell unless you're in a really exotic situation, because it really isn't necessary and is likely to cause failure. Liners, though, so if you do need to slow down, or if you need to basically stop the movement of water in a particular direction for whatever reason, liners are frequently used in that condition. And so you can see an example there where this cross-section out of the 2012 LID manual is intended to prevent water from migrating in under the structural material, in under the curb and gutter there. And so there's a piece of liner kind of prevent the water from moving into that zone. Same thing here. We can talk about, places where we don't want to infiltrate, like I mentioned, doing a large project. Seattle, where we have a steep slope, and for many blocks, all the facilities are lined, but then they also have orifice controls. So they're acting as kind of a hybrid bioretention, detention kind of line system that is put in to prevent basically combined sewer overflows in this basin. Underdrains. where we have a liner in place, clearly, we need to maintain aerobic conditions in the bioretention soil medium. So for the soil to be healthy and for it to meet the plant health requirements and for it to meet the treatment performance requirements, the soil cannot be saturated for long periods of time. So to maintain those aerobic conditions, we need to put an underdrain in. What we typically use for that would be slotted pipe, where the width of the slots are set to be smaller than the smallest piece of aggregate in our filter blanket. Bioretention soil, much finer soil, although more sandy and coarse than I think a lot of people expect, but still pretty fine. To choke it out of the pipe, we need to put in a filter blanket. And so we set the slots in our underdrain pipe to be such that we don't have the material from our well-graded filter blanket going down into the underdrain. And there's been some discussion about the why slotted pipe. Slotted pipe has a lot of advantages over perf pipe, primarily in its ability to be jetted out. PVC pipe, with the turned upside down, with the holes oriented down, because if the holes were oriented up, we've got problems of the aggregate falling through the perforations. But if we flip it over and we have perforations facing down, where water could migrate up in, that would work, except it's a little more problematic when you go to jet that pipe out. If you really want to clean that sediment out of your pipe, and so that is part and parcel of a lot of the designs we're doing, and in particular, again, to reference Seattle, we're doing some Seattle work where we actually are going to be commissioning the bioretention cells prior to their use, before we connect them to our underground injection control well. There's a commissioning and flushing period that needs to happen. And so anyway, the ability to easily clean out the accumulated sediment in the underdrain is kind of a key part of the design, which kind of drives us to basically slotted pipe. Sorry, I don't mean to belabor that point too much, but it's been a point of discussion in other settings. So there's our slotted pipe, and then in the image below the pipe, you can see on the right's the bioretention soil, and on the left is the kind of what is really the basis of design for our region. For the bedding material that needs to go on top of the underdrain is based on a City of Seattle gradation called mineral aggregate number type 26, and you can see it there in the lower left. And so that material is set up to be on top of the slotted pipe below the bioretention soil. There are some WashDOT analogs to type 26 that are a little more widely available up here that you can use, but mainly, point being, you use a sandy gravel material on top of your slotted pipe, and once again, no filter fabric. So then we place the underdrain pipe below the cell or up on a shelf like we talked about, as long as you maintain 18 inches of soil above that piped aerobic. Then you want to make sure that your pipe is surrounded by gravel, and there's some criteria there, 6, 12, and 12, about the kind of amount of that material that you need to have around your underdrain. So we discussed, so really, slotted pipe is considered superior to perforated pipe, and again, it's a lower potential for clogging and root intrusion, and just mainly its ease of jetting. While we heard that the downtown improvement gardens don't have cleanouts, typically we do recommend having cleanouts on the underdrains for observation and for cleaning. And in fact, when you get into tricky situations like, again, connecting to an UIC well, a lot of times we have an upstream and a downstream cleanout, and the downstream cleanout it has the ability where we can basically use a pipe plug inside the structure, plug that underdrain and jet from one end, and be able to jet from one cleanout to the other without running that silty material into our UIC well. So there's I would say that typically one and sometimes two cleanouts if you want to really protect your UIC well from contamination during maintenance. We usually like to see 0.5% on those underdrains. So we're looking at the surface of the bioretention cell typically to always be flat, but we can throw 0.5% on our underdrain. When we're orifice controlling them, a 1/2-inch orifice is usually the practical small end, but you'll probably find that a 1/2-inch orifice is probably too big. It's problematic. Given how small these cells are and how small the typical contributing areas are, 1/2-inch orifice can be difficult unless you're stringing a whole bunch of them together. And then certainly when we get down into small orifices, providing maintenance access so that they can be easily inspected and maintained is key. Adaptive management, like we heard, being able to cap your underdrain as needed, or being able to dry fit an orifice cap with a hole drilled in it can also be another way to do adaptive management. So if you realize maybe it didn't work out the way you want, or situations changed, designing for the ability to change the operation in the future can pay off in spades. Here we go again. This is an example showing what the underdrain, how the underdrain kind of fits in the cell here, again from using Seattle's standards, showing the type 26 mineral aggregate kind of all the way around the pipe. They're showing a foot above to really, again, separate those materials. Overflows. So we saw Beehive Grate overflow a bunch on the downtown improvement gardens, as you're seeing here. This is actually a case you can see where the overflow structure is actually being integrated in with a line system. So you've got your batten strip pinning the liner to the structure to kind of maintain that waterproof connection there. Again, there's a lot of different ways to provide overflows. Besides a beehive, you can do little weirs. You can put a cell that can spill to the next cell. You can put in those trench drain systems. You could do curb cuts. There's a whole bunch of different ways, but the beehive is usually the more common one. But every cell needs to have an overflow, in some fashion, whether it's a little low edge on a rain garden that we have in kind of a controlled overflow. They're all important. So yeah, we set the overflow elevation at the max ponding depth. And so if our cell wants to have 6 inches of ponding, then the rim of our catch basin should be sitting 6 inches above the top of our mulch. And then, of course, it's directed someplace else, downstream, what have you. There's all different criteria for sizing the system. So if we're doing, like I mentioned, this sort of simplified sheet flow overflow that you're seeing there in the rain garden, where we see it's a simple residential rain garden, and it's just intended to overflow there, kind of looks to the sidewalk or something. So we just have a planned, so if it overflows, where's it can go, or the exit curb cut trench. So we got curb cut in and we can have curb cut out, and then we don't have to deal with any piping or structures in the cell at all. So it's just different ways to do it. The beehive, like we see, vertical standpipe is another one where we can simply, if you've got a relatively small cell, you don't want to go through the expense of putting in a type 1 catch basin, you can just run like a 12-inch PVC up to the ponding depth and then just throw a cast iron dome on top. So there's a lot of different ways to provide that overflow. And then they can be strung together. And so the roadside cells are very often strung together like that, where we're working in a long linear fashion. You can see there where the pipe overflow from one cell just becomes the inlet to the next, and on you go. Or they can be single cells, all different configurations. The slope is the one that once you start getting into design, that's the one that you'll end up, I think, you deal with quite a bit. We're looking at a condition in Broadview Green Grid where we're dealing with a cross slope. So we got the road above, and then we're trying to build a cell on a slope. So we need to facilitate a flat rectangular area there to do our ponding and our infiltration. And so how are you going to deal with that? You got to cut on one side, kind of maybe fill on the other. You're creating a little rockery berm. This is something we spend quite a bit of time on the advanced class, is actually doing designs on slopes and really understanding how those slopes affect the actual cell area that's available to work with, and meet all of our other requirements for slopes and ponding depth. Getting the cells in series with a check dam or weir between is a nice way to go. So yeah, this is just a diagram showing you got your ideal zero cross slope versus how much reduced area that you end up having to work with when working on a cross slope. And then working on a longitudinal slope, you start getting into weirs if you're going to have a long continuous design. So you want to create a series of flat bottom cells. It'd really be great if all our sites were just 2% longitudinal, but they're not. Once we start getting above 8, we start doing a lot of construction work for a relatively small amount of bioretention cell area available. So it's not that the max and mins or optimum and the max there are really it's not a hard limit. It's just that you're going to have a serious case of diminishing returns. If you start doing these cells on much steeper slopes, you're going to be building a lot of weirs for the area that you end up creating. So Seattle also has this design where we're using overflow weirs as rock dams, kind of check dams in a system where you can see they actually have a sloped bottom in those cases, but the water, anyway, it's just a different way to go. We typically like to see flat bottoms, but sloping can work. Check dams and weirs, you can use those to facilitate grade, to set the overflows, wood, rock, concrete, vegetated hedgerows. Here's an example of using earthen berms up in High Point, or just by some careful grading, we kind of create some tiered systems using the kind of, I guess I would call a kind of washed septic drain rock, or you can see in the diagram actual wood weir. And then you can have a whole series of little ones, little concrete weirs. Sometimes they're precast, sometimes they're cast in place. And then there you can see the dome, got the dome grate overflow at the end. Again, just more examples of what these weirs can look like. 110th Street Cascade. Some of these, I think those are precast. Or the Beehive, as we saw a few times, with a little erosion rock around it. Pretty straightforward design. And here again, yeah, so these are the check dams. This is, again, out of our San Francisco work. We've got check dams that are actually keyed into the planter walls, where the check dams are also providing the kind of lateral restraint to those planter walls. And then you can see we had to think through how to provide the underdrain through those walls. And so we're kind of intentionally, you see the detail in the section there. So a quick run through some design information. Yeah, so the question is about cast in place versus precast on the weirs. Personally, only designed one with concrete weirs myself, and we did them precast. So they were set in a earthen, so it was soil all around. We weren't trying to tie into anything. So we were pretty certain that we could just come up with a standard module and then just be able to drop them in. And I do, intuitively, it seems to be where you can make that happen. It seems to be worth it.